In this video, we're going to be looking at harmonics. So you may remember that one bump is half a wavelength. So in the fundamental frequency, whenever we got a string tied down on both ends, remember we're going to have a node and a node there, and the lowest frequency we can have, or the smallest part of a wave, is therefore half of a wavelength. So this length is therefore equal to half of a wavelength. So if we solve that for the wavelength, we find out that the wavelength would actually be twice as long as this length. If we plug into our wave speed equation, we find that our velocity of our wave will be the frequency times 2L. If we solve that for the frequency, we'll find that the velocity is, if we solve that for the frequency, we find that the frequency is the velocity divided by 2 times the length. This is what we call the fundamental frequency. Now let's look over here at the second harmonic, or what's called the first overtone. For that, the length is one wavelength because we've got the two bumps here. So therefore, that's the easy one. Therefore, the wavelength is equal to this length. If we plug that into the wave speed equation, we simply find that the velocity is equal to the frequency times the length. And then if we solve that for the frequency, we get that the frequency for the second harmonic is the velocity divided by the length. So we notice that if we compare this velocity, this frequency to this frequency, we get twice the frequency of the original fundamental frequency. You're going to be left with completing the rest of this and filling out what the third harmonic is equal to. And hopefully you will see a pattern here. Make sure to notice what that pattern is. And finally, a tube open on both ends has the same pattern as a string tied down on both sides because they have similar geometry. So once you know the pattern for a tube open on both ends, that'll be the same pattern as you discover here for a string tied down on both ends.